All right, so now we're going to take a look at a few problems in which we are looking at work as represented by a change in energy. So this can mean that work is being done on an object when there is either a change in potential energy or a change in kinetic energy. So part of your task when tackling these types of problems is determining what kind of change in energy is happening, because that will change which type of equation you use. So let's take a look at some examples. Okay. So if some lifts a 10 kilogram bag from 3 meters to 5 meters, how much work is done on the object? So let's take a look at this question. He is lifting a bag. So if he is lifting a bag from one height to another height, we are dealing with gravitational potential energy. So in this case, we are dealing with, work being a change in potential energy, or EP. I can also expand this to, I'm going to do PE final minus PE initial. And I can even expand that further to MGH final minus MGH initial, or you can factor out those MGs so that you have MGHF minus HI. You may actually even see this equation sometimes looking like mg delta H. Okay, so that is a way to simplify something like this into showing us all the variables that you're actually going to need to deal with. So in this case, let's see if we're actually given any of that information. We are given the mass, and we're given that mass in kilograms, which is exactly what we want. We also know gravity. Gravity equals 9.81 meters per second. And we also know the change in height. The change in height is HF minus HI, or 5 minus 3, or 2.0 meters in this case. So that means I can simply plug in mass times gravity times 2.0, and I can calculate it. So I'm given 196.2, and since I want to put this to the correct number of significant figures, I'm only going to have two significant figures. So if I were to round that up, it would be 200, but that is only one significant figure, so I would have to do 2.0 times 10 to the 2 joules in order to properly represent two significant figures. All right, so that's a bit of a review from Unit 1. I know it's been a while, but this is what your answer should look like. Okay, now I'm going to use a slightly different example. All right, if Ali, so now we're looking at Ali pulling a 25 kilogram cart up a ramp that is 1.5 meters tall. So this height is like this. What is the work done on the object? So in this case, we are going from an initial height of 0 to a final height of 1.5 meters. So we can actually go back to what we did before, which is work equals change in potential energy, which is final potential energy minus the initial potential energy. And all the work I did up top led me to say mg delta H. So the work I'm doing is a change in the potential energy. So if you remember from the last video, I had a force applied over the ramp, and I was measuring the distance of the ramp. However, I'm not given this distance of the ramp. I'm also not given any means to calculate the distance of this ramp. I'm also not given a force. So in this case, that's where I want to be looking at the change in potential energy, because the work that is being done on this cart is actually changing its potential energy. It's taking it from a lower height to a higher height. It's taking it from even if it was going from a higher height to a lower height, there would also be work being done on the object. But the main thing you need to keep in mind is that the change that is taking place in this scenario is that the cart is changing its gravitational potential energy. So if I go back to these variables, I can ask myself if I'm actually given the information to now solve. My mass is 25.0 kilograms. My gravity is 9.81 meters per second squared. And, oops, I didn't put that up top. And the height is 1.5 meters. Now I'm in a position where I can actually solve this. My mass is 25. 9.81 meters per second squared is my gravity. My height is 1.5. Now I can solve this. 25 times 9.81 times 1.5. I'm dealing with 367.875. And since I want, in this case, only two significant figures because of that, I'm dealing with 370 joules of work being done on that cart to take it from a lower gravitational potential energy to a greater gravitational potential energy. Okay, so those are two examples in which you were looking at the change in potential energy. Now I want to go through two examples in which you are looking at the change in kinetic energy, and that will have to do with a change in the speed of an object. So let's take a look at what's happening here. Whew, excuse me. A 2,500 kilogram car is traveling at 90 kilometers an hour. It skids to a stop. So how much work is done to make the car stop if it stops over a distance of 30 meters? So let's take a look. In this case, you have the speed of the object changing. If the speed of the object is changing, then you are looking at the work being done to cause a change in kinetic energy. Okay. So let's take a look at what changing kinetic energy is. Changing kinetic energy is our final kinetic energy minus our initial kinetic energy. So that means we can analyze both of these individually. So let's take a look at this. I'm going to do half mvf squared minus half mvi squared. Something that's kind of useful in this scenario is that we know that our final velocity is 0 because our car stops. So if our vf equals 0, that makes this whole thing 0. All right? So that means we are then dealing with minus half mvi squared. So we can actually plug in this information because I'm given the mass. My mass is 2,500 kilograms, and I'm given the initial velocity, which is 90 kilometers an hour. One thing to keep in mind is you do have to convert that to meters per second. So that would actually be 25 meters per second. So I can plug all of that in, and 2,500 VI is 25 squared. I'm going to plug that in. And I have about 781,250, but I know I have 2 sig figs from that. So I'm actually going to say this. So it's 780,000 joules of energy, or 780 kilojoules. And yes, it is negative because the work being done is to slow it down. But unlike, whoops, that's off the screen. This is actually a scalar quantity, which means it's not taking direction into account, but that negative sign is telling us that it is causing a decrease in that speed. It is not causing it to increase speed. So keep that in mind, but it is a scalar quantity. So I will just rewrite that up here. 780 kilojoules of work is being done on that car to make it stop. Okay? Now let's take a look at my final example with you guys, and I'm going to, for all you hockey lovers out there, I'm going to keep in mind that I know nothing about hockey, which means I don't know how fast these hockey pucks actually travel or how much the hockey pucks actually weigh. I just put in some numbers. I apologize for all of you guys who do know hockey a lot better than I do. But that doesn't mean we can't solve this problem, whether or not my numbers are correct at all. So, a hockey puck is moving at 3 meters per second and is hit by a player. The puck reaches a final velocity of 10 meters per second. How much work is done on the 3.5 kilogram puck? So in this case, again, we have a change in speed, which means the work being done is resulting in a change in the kinetic energy, which is the final kinetic energy minus the initial kinetic energy. And so if I broke that down, I would have my final kinetic energy minus my initial kinetic energy. And what I can do is plug in all my values because I have them all. My mass is 3.5 kilograms. My VF is 10 meters per second. And since it's already in meters per second, I do not need to convert. And then my initial velocity is 3.0 meters per second. And also do not need to convert because these are all of the units I want. So then I can just plug all of that in. But to make it nice and easy, what I'm going to do is I'm going to factor out the half m so that I have VF squared minus VI squared. And then I can plug that in. So I'm going to do half 3.5. You don't have to do that. For some reason, I like to look at it that way. My VF is 10.0 squared minus 3.0 squared. So you get half 3.5, and I sometimes like to do some mental math. 100 minus 9, which equals half 3.5 times 91. Let's see what I get. I got 159.25. I only have 2 sig figs, so that would give me 160 joules. So the work being done on that hockey puck is 160 joules. All right, and so 160 joules is done on that hockey puck to make it speed up. So in this case, we were using a scenario in which something was speeding up. In the prior one, we were looking at a scenario in which the work being done on the object was forcing it to slow down. Either way, in both cases, there was a change in the kinetic energy, or in other words, a change in the speed of the object. Hope that was all useful. If you guys have any questions, you'll all know where to find me, and good luck.